Our next notes we're going to be talking about is a special type of equilibrium constant called KSP. And whenever you see K, it means equilibrium constant, and this stands for solubility product. Constant. So if you hear to somebody talk about KSP, they're referring to the equilibrium constant of a salt dissolving. So let's consider salt dissolving. So what we talked about before, we talked about salts dissolving in terms of soluble or insoluble. So now that we know about equilibrium, we can talk about how soluble a salt is. How soluble versus soluble or insoluble. So what we talked about before is we consider something soluble. Like if we added let's say we have some water. We added some NaBr, sodium bromide. We added a small amount. What will happen is that salt will dissolve into its ions, its positive ions and its negative ions. And they will separate in solution. Now, if we added, so it would separate into Na plus aqueous plus Br minus aqueous. So our reaction is NaBr, solid, and that's the positive ion is the Na and the negative ion is the Br. Makes Na plus aqueous plus Br minus aqueous. Now, this is considered soluble because we only favor the forward reaction. It's highly favored. Now, this is what they call a strong, so if you talk about in terms of K, EQ, the K for this reaction is equal to concentration of Na plus times the concentration of Br minus. So they call this, since it's a dissolved salt, NaBr, they call it the KSP. So this will have a high constant since it's mostly dissolving. So what they call this is a strong electrolyte. Where you have a lot of salts dissolving. Now, we have a slightly soluble salt. Let's say we have, for example, AgBr. Now, this is, so we talked a little bit about it when we talk about weak acids, but if we added a small amount of AgBr to a solid, well, what would happen is only some of it would dissolve. Like you'd have your positives and your negatives still in solid formation. And we'd have some becoming Ag plus and Br minus. That's our AgBr solid right here. And some would be coming Br minus. But also you'd have these coming together forming back AgBr solid. So there's an equilibrium here. AgBr solid becomes AgBr, Ag plus aqueous, plus Br minus aqueous. But also the reverse reaction happens as well. So we form an equilibrium. And this has a low KEQ. A low equilibrium constant. It's actually 5.0 times 10 to the negative 13. So what will happen is, once we have what they call saturated, that means the most will go into solution. We'll establish an equilibrium. And no more will dissolve. So, say something called the solubility, and that's a general. So the solubility is defined as the most amount of solute that will dissolve in aqueous solution. You can talk about it in moles per liter or in grams per liter. So, let's say I want to talk about, let's stick with our example. Let's talk about our example of AgBr. So we have this equilibrium forming, AgBr solid in equilibrium with Ag plus ions plus Br minus ions. So the equilibrium constant for this, Ksp, is equal to the product of Ag plus ions and Br minus ions. That's why they call it the solubility product constant, because we're multiplying those together. So let's consider, what is the solubility? So we could actually use a Rice diagram. It's a little simpler, but I like to keep it the same way. So our reaction is the same, AgBr solid in equilibrium with its ions. So we can actually treat these the same way. So our initial, and I'm going to draw a line through this since we have a solid right here, which is not involved in equilibrium constant. So assume we have nothing starting out dissolved. We're going to increase the amount dissolved. So our equilibrium constants are x. So we can pretty much solve this out pretty easily, knowing the Ksp up here. We know the Ksp is 5 times 10 to the negative 13. So we can say 5.0 times 10 to the negative 13 is equal to x times x. So, and if we can easily solve this, this is a fairly simple problem to solve, and we can solve for x, and that x is equal to 7.07 times 10 to the negative 7 moles per liter. So that's in molarity when you solve for it in Ksp. You can easily convert that to grams per liter if you wanted to. Sometimes you'll see it in terms of that. So 7.07 times 10 to the negative 7 moles of AgBr, that's AgBr aqueous, per 1 liter. And if you want to solve the solubility in grams per liter, you can just, multiply by the molar mass. Use dimensional analysis. Moles AgBr, grams AgBr. And we all know off the top of our head that the molar mass of AgBr is 187.8 grams per mole. Just kidding. I calculated that ahead of time. We can also predict if a precipitate will form or not. So essentially it's the same thing. We can predict if a precipitate will form based on molarities or concentration of the ions in solution. So let me write down the equilibrium, AgBr. And this is a couple things you guys are always going to want to do when you're doing these KSP problems, is write the equilibrium and the K expression, which you should probably already be in the habit of doing. And the KSP is equal to 5.0 times 10 to the negative 13. So if we're asking if a precipitate is forming, we're talking about the reverse reaction here. The reverse reaction is precipitation. The forward reaction is dissolving. So if a precipitate forms, we're asking really, will we favor the reverse reaction. And the real question is can be answered just like we did before. We can figure out what reaction will be favored. We do a test. Let's say, for instance, will a precipitate form if the concentration of of Ag plus equals 2 times 10 to the negative 3, and concentration of Br minus is equal to 4 times 0.0 times 10 to the negative 4 moles per liter for molarity for both of them. So what we want to do is similar to how we did other equilibrium problems. We do a test of our Q value. So in this case, Q is equal to 2.0 times 10 to the negative 3 moles per liter, and times 4.0 times 10 to the negative 4. This is just our test conditions. We're just seeing what we have. Our concentration of AgBr is 2 times 10 to the negative third. Our concentration of Br is 4 times 10 to the negative fourth. So we just plug in those values for what we have. And we're going to compare our conditions to the KEQ, or in this case, since we're talking about specific type, the KSP. And what we get for a value here is 8 times 10 to the negative 7. So our Q in this case is greater. Our Q is greater than our KSP. And I'll just abbreviate that. 8 times 10 to the negative 7 is greater than 7, or whatever it is, 5.0 times 10 to the negative 13. That's our KSP for AgBr. So it's much greater, so we will favor reverse reaction. So yes, a precipitate will form. So we'll move on to talk about more of the stuff later.